Okay, vector spherical harmonics. So we know the definition of gradient. The gradient operator is defined like that. Derivative with respect to r, derivative r with respect to theta, and derivative r sine theta lambda. Now let me use this gradient, apply this operator to the spherical harmonic expansion of a field. Let me call it, for example, for t. So the gradient of t, the spherical harmonic expansion, will be, if it is from 2 up to infinity, m, I will write it here. So derivative of this one, r over r, m plus 1, t and m. So this, let me write it like that, so it is simpler. It's er plus e theta plus or ex, e lambda. Doesn't matter, you can call it xy, it doesn't matter. So er, then plus 1 over r, m plus 1, t and m. Oh, I missed y and m here. Y and m here. The rho on the theta, e theta plus rho y, no, sorry, 1 over r, m plus 1, t and m, sinus theta lambda, and e lambda. So this is a spherical harmonic expansion of the gradient of the gravity potential the gravity disturbance. So here we define the vector spherical harmonics like that. Let me clean this part. Vector spherical harmonics are shown by x and m1, theta and lambda will be the same with y and m, theta and lambda. And x2 will be x and n, m2, theta and lambda will be here, round y and m, round theta, e theta, plus y and m sine theta, a lambda, e lambda. So let me clean the point below. And these spherical harmonics are orthogonal too. But how? We have already discussed about the orthogonality properties of the spherical harmonics. And now I have this one for the vector spherical harmonic, and m theta lambda. That is inner product, is I call it here. Then we call I prime and m prime, theta and lambda. This is sigma. So it is like that. 4 pi delta n prime delta m prime delta I and I prime. And the other one will be 4 pi n multiplied by m plus 1 and m prime, m prime, and I prime. This means that if I multiply the spherical harmonic, the first type, 1, to the second one, it will get this one 0. If we get it, they are orthogonal. And if I multiply the first one by first one, then I get this value. If I multiply the second one by second one, I get this value, not only 4 pi. So based on this definition for this orthogonality or orthogonality, then we can solve the boundary value problem of astrogeodetic boundary value problem. How? Then I expand. I can simply write the equation like that. To infinity, and I have 1 over rn plus 1 tnm 2. So what it was, we have already definition of them. We have it. So I can expand this geodetic data in terms of the vector spherical harmonic of the second type. So let's assume that we are at the surface. It means that r is equal to r. Then this equation will be simplified to this 1 over r 2 x and 2 theta. And the question is, if I want to determine t and m, or I can change it to the geoid. I can write it n, m, and I put a gamma here. Both are possible and similar. So I write an m, which is easier for you to digest it. Then I put it in m. I want to determine an m from this equation, but since I have the derivative of the spherical harmonics inside this one, I cannot directly use the orthogonality property of the spherical harmonic, but I can use the orthogonality property of the vector spherical harmonic. How? I will write integral sigma e theta plus e lambda inner product spherical harmonics of the second type theta and lambda prime. I will that prime is integration point. The sigma equals, I continue down there, r sigma m from 2 to infinity m minus 10, and here I will write n m spherical harmonics of the harmonic coefficients of the gravity, and I write the integral of x m prime second type theta prime lambda prime, and y and m 2 theta and lambda the sigma. So that's really nice, because now, because it's inner product here, this equation will be 4 pi delta n. Oh, sorry. Missed. This equation will be 4 pi n multiplied by m plus 1 delta n prime delta m n prime. So then it will be simplified more. Therefore, I can simply bring this to the other side for 4 pi, the other side, and I can write, okay, then I can write simply that spherical harmonic, oh my god, spherical harmonics of an m hour r over 4 pi gamma. So r integral of sigma prime epsilon tri kc eta prime theta prime lambda prime. Yes, we got the formula. However, this is for the spherical harmonics, coefficients of the geoid. So, but it's not finished yet, because we can expand this function a little bit more to see what the details. 4 pi gamma will be integral of then epsilon theta here, and this one was derivative of this, if you remember, theta plus derivative of y and m sine theta lambda e lambda d sigma. So if I multiply this one is multiplied this one. E theta is multiplied by e theta, it will be 1 because they are orthogonal. And the result will be r 4 pi gamma integral of kc derivative of plus eta prime, the first one to the second one. E theta and e lambda are orthogonal, they will be 0. Then no discussion. And eta prime, the second term, this one to this term, this will be 0 as well, because e lambda or e theta are orthogonal. Then this remains that the last ones, e lambda to e lambda will be 1. Then 4, I can write simply y and m sinus theta lambda d sigma. So this is the spherical harmonic expansion, the integral of spherical harmonics of the geoid from the deflection of vertical. Good. So now I am going to go back to the special domain from this equation. Let me clean this part first. Oh, I think I missed one thing here. It should be here. Should be we should have uh, 4 pi gamma n plus 1. So now I'm going to the spherical. I take the spherical harmonic synthesis of both sides. It means that I get summation from 2 to infinity m is n m y and m theta and lambda. So here we are at the integration domain, then it will be theta prime. So I take the same on the right side. So I come to 1 over 4 pi gamma, and n should be inside the summation if I take it. So this will go out. Then I will write the integral summation of from 2 to infinity, and the m minus 1. And here I will have my prime and m theta prime lambda prime plus, I will write the rest here, c prime y and m theta prime lambda prime sinus theta sin lambda prime, and the whole is multiplied by y and m theta and lambda. Now I can clean the and of course one integral. So I do not have this, I do not have the relation between these things, but I can write it like that. Summation minus n up to n, derivative of theta prime lambda prime, and y and m. I have something one here, and I have a similar one here. Y and m theta prime lambda prime sine theta prime lambda prime, and again y and m theta and lambda. So if we didn't have this derivative with respect to theta, it would be addition theorem. Now we have it. It will be then addition theorem, derivative of this p respect to p cosine, and the same here. Then it will be derivative of pn cosine divided by sine theta and lambda. Therefore, based on this addition theorem, this formula that I have written above can be simplified to the left-hand side will be the geoid, and our right-hand side 4 pi gamma is going to be in there, and let us keep this some integral integral and the summation. And we have already had 1 over n plus 1. And now we have the addition theorem instead of this harmonic. Then it comes here. Then I will have 2n plus 1, which is common in both. And I can write sigma n. It is rho pn rho theta. Cosine theta plus eta on the pm on the cosine sine theta d sigma. Also, it is not difficult to prove that let me write it with another color. This one, rho pm rho theta cosine theta will be rho the pn rho the psi with rho theta. And the same thing for pn cosinus theta sinus theta rho the pn on the psi by rho lambda. This will be, I think, rho pn rho psi. I think it should be sinus theta around the pn. I will check it now. Oh, sinus is here, sinus theta, it's alpha, and it will be cosine alpha. Let me check the formula. Okay, the first one is cosine, the second one is minus sine. The first one is cosine, and the second one will be minus sine. So what is alpha? Alpha is azimuth. Azimuth between computation point, which we have n, we want n at it, and the integration point. For each the point that we have psi and x. So you can simply, based on this definition, you can simplify your integral formula to this. N to the geoid will be r over 4 pi gamma integral of this is 2, okay, 2n plus 1 n plus 1 root p root psi cosinus psi. Then here you can simply write you see at integration point the cosine alpha minus sine the sinus alpha the sigma.